SwayamPrabha. Digital India. Educated India.
Hello everyone. So we'll be continuing by looking at the module scales of turbulent motion. In the last class, we were dealing with the spectrum function, the energy spectrum function. We looked at the 1D spectra and looked at it in terms of K kappa eta, right? And saw what that meant, looking at the different ranges, the inertial sub-range, the energy containing range, then the dissipation range, and how the value of kappa eta varies in these ranges. We looked at that. We even looked at the 1D spectra and tried to derive relationships for the universal non-dimensional function, the Kolmogorov's spectrum function on the right? And that came from Kolmogorov's hypothesis. So now let's go further by looking at this energy spectrum function in the inertial subrange. Okay. Now in the inertial subrange, according to the second similarity hypothesis, E of kappa, it has a universal form which is uniquely determined by epsilon and is independent of nu, isn't it? So in that sense, so here what happens is the psi, as in the spectrum function, the universal spectrum function that we had earlier, which was this one, we took it to be independent of nu, isn't it? So that is why we don't have a nu in here, we only have epsilon, and that is applicable to the inertial subrange as I had mentioned yesterday. So here what happens is this psi of kappa eta becomes independent of its argument and hence tends to be a constant, because see what happens. What we are saying is in the inertial subrange it only depends on epsilon and is independent of nu. So this is what you have. Here it depends on epsilon already, which means this right here has to be a constant because your epsilon dependency is already there. So your psi has to be a constant, isn't it? So if psi is a constant, that is what we are saying. It becomes independent of its argument and hence tends to be a constant. So essentially, according to the second similarity hypothesis, your energy spectrum function is this one. C epsilon to the 2/3 and kappa to the minus 5/3. This was basically psi of kappa eta. And what we are saying is psi becomes a constant because it only depends on epsilon, as in the energy spectrum function. So in that sense, the energy spectrum function is C epsilon to the 2/3, kappa to the minus 5/3, and that's it. This is actually the famous minus 5/3 Kolmogorov spectrum. The fact that the energy spectra varies according to kappa to the minus 5/3. This is universal. This is applicable to all turbulent flows, no matter what kind of turbulent flows you have. And C here is a universal constant. It's a universal Kolmogorov constant, because remember, when we wrote the energy spectrum function, we wrote it in terms of psi of kappa eta, and we did say that this would be a universal function. Turns out that is going to be a constant because your dependency of epsilon is already there in the energy spectrum function. And that's the only dependency you have. Obviously, kappa is there, but other than that, epsilon is the only dependency you have. It does not depend on nu, which means your universal spectrum function, the Kolmogorov function psi, becomes a constant. Okay. Now, experimental data supports the fact that this C is 1.5. It actually comes out to be 1.5. In which case, you will have the 1D spectra, because remember we wrote E11 and E22 in terms of E of kappa. So once you know that this is your energy spectrum function is fixed, E of kappa, we can derive equations for E11, which is, this is what it looks like, and E22, where you have C1 as the constant and C1 prime as a constant, and these values, C1 is going to be 18 over 55C and C1 dash is going to be 4/3 C1. Where did I get that from? I had derived this as well earlier. If you remember, this one here, C1 is to C1 dash is to C, is C1 is to 4/3 C1 is to 55 over 18 C1, which means that is how I'm getting the 18 over 55 and the 5 over and the 4 over 3. So here what I have is C1 dash is equal to 4/3 C1 and C1 itself is equal to 18 over 55 C. Because earlier I had derived that C is 55 over 18 C1, isn't it? Here what I had is 55 over 18 C1. And where did that come from? That came from the fact that C1 is C1 dash is half times 1 plus P. We had derived this in the last class. And C is half C1 P times P plus 2. So all that leads to these ratios of 4/3 and 55 over 18. That is where I'm getting it from. Okay, so what I have is C1 equals 18 over 55C and C1 dash equal to 4/3 C1. So I have now the 1D spectra fixed once I have fixed the inertial subrange spectra. So I have the energy spectrum function for the inertial subrange, which is C epsilon to the 2/3 kappa to the minus 5/3. And remember, C is a universal constant to be, and it turns out to be 1.5 based on experimental data. And then I use the earlier equations to calculate E11 and E22, where their corresponding constants are 18 over 55C and 4/3 C1. I hope this is clear. We now go into the model spectrum. A model spectrum is something that is constructed to match the spectrum of a turbulent flow. So what is shown here is the model spectrum, and it is normalized with certain values. So E of kappa is U eta squared eta. If you remember, this right here was our psi of kappa eta. We had this earlier when we wrote the energy spectrum function. See? And what I'm doing here is I am plotting essentially psi of kappa eta, which is going to be a universal function, isn't it? So that's what I'm plotting. E of kappa divided by U eta squared eta. So if I do that, this is the formulation that I get. And this is a model spectrum. That means there is a function associated with it, and that function is given here. C epsilon to the 2/3 kappa to the minus 5/3. This is coming from the inertial subrange. ISR, as I was calling it, inertial subrange. And then I have two additional functions, FL of kappa L and F eta of kappa eta. FL and F eta are non-dimensional functions because, as you can see, this depends on kappa L and kappa eta. L has units of length and eta also has units of length. Kappa has units of 1 over length. So this will be non-dimensional functions. And this corresponds, the C epsilon to the 2/3 kappa to the minus 5/3 corresponds to the inertial subrange. So a function like this will give me a curve as shown in this figure. Now what is FL and F eta? Of course, those have to be specified as well. So that's what we mean by FL and F eta are specified non-dimensional functions. It turns out it looks like this curve has a slope of 2 in the energy containing range. It has a slope of minus 5/3 in the inertial subrange. That is expected. And some steep gradient in the dissipation range. So this turns out to be the energy containing range. This turns out to be the inertial subrange, ISR. And this turns out to be the dissipation range. So minus 5/3, that is fixed. We already showed that in the previous slide. So let's go into detail into this model spectra and look at what FL and F8 are. Now, the function FL determines the shape of the energy containing range. And what we should want it to do is that we should want it to tend to unity for large kappa L. Because what should happen is we want the inertial subrange spectra to be recovered in the inertial subrange. So we want this to be 1 as soon as it gets into the inertial subrange. Same goes for F8, and I'm coming to that as well. We want FL to tend to 1. So that is what we mean by FL tends to unity for large kappa L. And similarly, F8 determines the shape of the dissipation range, and it tends to unity for small kappa eta. So what is essentially happening is F8 is sort of deactivated in this range. And FL is deactivated in this range. Am I making sense? So the FL is deactivated in the inertial subrange and the dissipation range. The F8 is deactivated in the energy containing range and the inertial subrange. When I say deactivated, they will have values that are closer to 1. So it tends to unity. So in the inertial subrange, both FL and F8 are essentially unity. In that sense, you will, so by that token, Kolmogorov minus 5/3 spectrum is recovered that way. Now, how do you specify FL? There is a way to specify FL. FL of kappa L is kappa L over kappa L squared plus CL, the whole thing to the half. This whole thing raised to 5/3 plus P naught. Now, the P naught value is taken to be 2 and CL is a positive constant. As you can see, the FL tends to unity for large KL. How is that? Because for large kappa L, this CL drops out. CL drops out because it is very small compared to kappa L, so it drops out. Then you have, so when kappa L is much greater than 1, then what you have is kappa L over kappa L squared raised to half, this whole thing raised to 5/3 plus P naught. So then this turns out to be 1 for large kappa L. So you will have the exponent of 5/3 plus P naught leads to E of kappa varying as kappa to the P naught. What happened to the kappa to the 5/3? What happened is there's the inertial range spectrum that is there, which is kappa to the minus 5/3. That minus 5/3 and the 5/3 from here cancels out. So you're left with just kappa to the P naught. Again, this is once CL drops out. Okay, this is once CL drops out. So then you will have kappa to the P naught. So for P naught equal to 2, you get kappa squared. This is for small KL. With the alternative choice of P naught is equal to 4, the spectrum becomes the one common spectrum, or E of kappa is equal to, approximately equal to kappa to the 4 for small kappa. So what happens is FL tends to unity for large kappa L, while the exponent 5/3 plus P naught leads to E of kappa varying as kappa to the P naught, which is equal to kappa squared. So for small kappa L, what happens? For small kappa L, this drops out, isn't it? So when kappa L is much less than 1, then what you have is you will have CL on the bottom, on the denominator, which is a constant. So ignore that, but then you will have kappa to the 5/3 plus P naught. And this kappa to the 5/3 and a kappa to the minus 5/3 cancel out. So you essentially have only kappa to the P naught. That is what we mean by this. And if P naught is 2, it is kappa squared. If P naught is 4, it is kappa to the 4. So the spectrum becomes the von Karman spectrum, which has E of kappa, which is approximately equal to kappa to the 4 for small kappa. Now, let's go to F eta. F eta has this function. It's an exponential function. So here, what you have is beta and C eta are positive constants. So for C eta is equal to 0, let's say you want to simplify the function. Then you can assign C eta is equal to 0, then you get this function here. F eta of kappa eta is exponential minus beta kappa eta. This makes sense that the dissipation range specification, we are providing an exponential function so that it is infinitely differentiable, because dissipation carries on for quite a few scales. Dissipation carries on even for the smallest scale and even lower than that, right? It just carries on for smaller and smaller scales. So that is what you want. That is the reason why we are providing an exponential function. So this means that for large kappa, the energy spectrum function decays more rapidly than any other power of k because of the exponential function, and hence the exponential decay. You can see from the model spectra that this is quite steep. That is because it decays with k much more rapidly than the other two ranges. The energy decays quite rapidly. That is why we have the exponential function. So we have an exponential function, and this is the simpler form of the exponential function. You have it as exponential minus beta kappa eta. And several experiments have shown that beta is approximately equal to 5.2. However, the simple exponential function departs from the unity too rapidly for small kappa eta. Okay, so in that sense, the value of beta is actually constrained, and specifically it is constrained to a value of 2.1. To avoid all of this, you can just use this function here. It's slightly more complicated, but it does not depart from 1 too rapidly. Okay, whereas this one here departs from 1 quite rapidly for smaller value of kappa eta, because we want it to be 1, right? We want it to be 1 so that you can recover the inertial subrange. You can recover the energy containing range alone. So we want it to be 1 for small kappa eta. But with this simplified function, it departs from unity too fast. So we can use the top one for better predictions. Now, overall, how do you specify this? This function depends on 3 values: the turbulent kinetic energy, the dissipation, and the viscosity. So for specified values of for specified values of k, epsilon, and nu, the model spectrum is determined by using C is equal to 1.5, and say if you want to use the simplified function, beta is equal to 5.2. Okay. Now, alternatively, you can use the value of R lambda. Okay. The constants CL and Ceta are determined from the requirements that E kappa and 2 nu kappa squared E kappa, they integrate to k and epsilon respectively, because this is the integral of that function. Energy spectrum function is the turbulent kinetic energy, and the integral of this one here, 2 nu kappa squared E kappa, is epsilon. So what you get is, if you integrate that to k and epsilon, then at high Reynolds number, their value is approximately 6.78 and 0.4, the CL and C eta values. So that is what you have. So this is using an R lambda value. Alternatively, you can just use the k, epsilon, and nu, and you can construct the model spectrum. The figure that we showed earlier for the model spectrum is a log-log plot, of course. You can see that here, it's a log-log on both sides. So it's a log-log plot, and it is the log-log plot of the model spectrum at R lambda is equal to 500. The power loss, as in E kappa, is approximately varying with kappa squared, and at low wave number, and E kappa varying with kappa to the -5/3 in the inertial subrange, You can see that easily, right? So you have a slope 2. Remember, it's going to be a line because you have it plotting as a log-log plot. So it will be the slope, it will be linear in the log-log plot, and the slope will represent the power of kappa, isn't it? So you have the slope of 2, that means it varies as kappa squared, and you have a slope of minus 5/3, that means it varies as kappa to the minus 5/3. Obviously, the dissipation range is exponential, so that's the way it looks. Now, let's apply this model spectrum to experimental data. This is a plot that I have shown earlier to illustrate several other examples, but this is actually where it comes. On the left-hand side, on the y-axis, I have the 1D spectra, which is E11, and I have normalized it with epsilon nu to the 5, the whole thing to the 1/4. If you notice, I am getting that from this one right here. Essentially, what I'm plotting is the non-dimensional psi of kappa eta. In the model spectra, when I showed the model spectra, I plotted E of kappa over U eta squared eta, isn't it? Which is again psi of kappa eta. I'm doing the same thing here. This is psi of kappa eta. Obviously, because I'm plotting the 1D spectra, I'm getting a different constant, but essentially I'm getting the same thing. I'm getting a universal function, E11 of kappa 1 divided by epsilon nu to the 5, the whole thing to the 1/4. This is plotted against, as you can see, kappa 1 eta. What is shown here? Multiple data sets are shown here. You cannot see the legend clearly, but there is wake flow involved, there is channel flow involved, there is flow over a flat plate involved, multiple kinds of data, and at different Reynolds numbers. What you can see is that I have a normalized function that is plotted, and what I should be getting is a universal function, psi of kappa eta, and it looks like I am getting a universal function. Look at what happens here. Universal function only in certain ranges. It is not in the energy containing range, because the energy containing range, this one, will depend on the flow. On the other hand, this is the inertial subrange, ISR. As you can see, this slope is 5/3, as in minus 5/3. It is minus 5/3. That line there represents possibly minus 5/3, and this here is the dissipation range. The energy containing range, I have different values, and that makes sense, because if you have different Reynolds numbers, if you have different kinds of flows, it depends on the kind of flow you have. It depends on the scale of the problem. It depends on the type of flow. So the energy containing range would be different. So all the symbols shown here in this plot, are experimental data. You can see some lines plotted as well. These lines are according to the model spectra according to the experimental data. So a model spectra has been constructed based on the data that it is compared against. It has been constructed and plotted alongside. And as you can see, there is almost an excellent match with the kind of data. So this line matches with that data, right? The data associated with it. And it matches exactly. Of course, there is some variation here, some minor variations here. But for the most part, the model spectra is matching the experimental data very well. And that is the power of this model spectra used here. You are getting an excellent match between the model spectra that we just showed, plotted on a log-log scale, and matching with the experimental data for different kinds of data. And a whole set of data are shown here. Over several years, experimental data measured at different Reynolds numbers. Another point to make from this data is that the function is universal from in the inertial subrange and the dissipation range. This is Kolmogorov's hypothesis. The fact that past the energy containing range, you have a universal equilibrium range. These two together is the universal equilibrium range, isn't it? UER, universal equilibrium range. The inertial subrange and the dissipation range, isn't it? The inertial subrange is varying according to the -5/3 slope, and the dissipation range is varying exponentially, it looks like, because the model spectra is matching it very well. So that is what you have. And one additional point, as I increase the Reynolds number, so these model spectra are for different data values, the different R lambda values, as you can see, 30, 70, 130, 300, 600 and 1500. And as the Reynolds number is increasing, the R lambda values, as the Reynolds number, the R lambda value is increasing, these curves are going higher and higher. That means you have more energy with higher Reynolds number. That makes sense. More fluctuations, more kinetic energy, higher level of energy with higher Reynolds numbers. And that you can see from the model spectra, and you can see from the experimental data as well. So that is what we have done. We'll go into more detail into this model spectra in the next class. But I hope this was clear. Thank you.